Oh dear, I see what I did. I didn't put in the decoupling capacitors. Hi, I'm Kevin. Welcome to my cave. Last time we were looking at transconductance amplifiers, which take an input current and translate it to an output voltage. We saw how to get a very large transimpedance, to use a tiny input current and get a usable output voltage. This time I want to get a start on transconductance amplifiers, which go the other way. They take an input voltage and produce a proportional output current. The simplest ones are the ones that are used just as adjustable current sources, with a control voltage setting the current. Let's look at those first. If you recall from last time, our transimpedance amplifier started with a basic inverting amplifier. We had some unknown source supplying a current into the virtual ground, and a resistor in the feedback loop. Whatever the unknown input current was, the feedback current had to match it. So Ohm's law tells us what the output voltage has to be as a function of the input current. For a simple transconductance amplifier, we have to interchange the input and feedback legs of the circuit. The input side is now a resistor connected to some input voltage, while the feedback path now contains some unknown load. As before, the feedback current has to balance the input current, and we can get the input current from Ohm's law. But we have a problem here. The input impedance of our amplifier is just the value of the input resistor. If that's low, then the amplifier is going to load the previous stage of the circuit. That's not great. But if it's high, then the circuit will deliver only a tiny current to the load. That's not what we want either. We could, I suppose, fix that problem by putting a buffer stage ahead of this amplifier. Or we could make a better choice for the circuit topology. Let's look into that option. We've learnt in our other episodes on the op-amp that the non-inverting configuration has a high input impedance, so let's try that instead. We'll still put our load in the feedback path, and we'll sync the load current through a resistor to ground. By the way, this resistor is often called the sense resistor, since its job is to detect how much current is flowing in the load. The golden rules of op-amps say that the op-amp will try to hold its two inputs equal, so the top of the sense resistor will be at the input voltage, and Ohm's law gives the current through it. And the load has to be passing the same current, because we assume that the op-amp inputs draw no current. Let's fill in some component values and see how this works on the breadboard. I have a schematic here, and of course I shared it on the project GitHub. There's a link down in the video description. I'm using a 100K pot to derive the input voltage, which will vary from -5 to +5 volts. The load itself is simply a 10K pot. I can twist it and see if the output current stays constant. The sense resistor is 1K, which will give an output current of 1 mA per volt at the input. I'll have my yellow meter looking at the input voltage and my blue meter looking at the output current. The op-amp is an LMC6482, which is a dual CMOS op-amp with rail-to-rail input and output. We'll need the rail-to-rail swing later on. I'm running the op-amp off of positive and negative 5-volt supplies. And of course I'm using decoupling capacitors. The unused stage is connected as a follower with a grounded input. That's usually the best practice. Okay, that should be good enough to demo. Time to breadboard it. Before we continue, let me interrupt for just a moment. Longtime viewers of this channel will know that it's always free to all comers. Nothing is ever paywalled. But I do end each video asking one thing, that you take care of one another. To that end, all the advertising revenue that I earn from this channel goes to charity. The current featured charity is called Heifer International. Heifer's mission is to end hunger and poverty in partnership with the communities it serves. It begins with a seed investment in livestock or agriculture, together with mentorship to help its participants build a business. The participants, small farmers, ranchers, and female business owners, are able to earn a living income and continuously lift up their communities as they train the next generation of leaders. I'd like to ask you to join me in supporting this organization. I set a goal of $500, which is enough to give a cow to a family in need, together with training and education in how to care for her and how to access the market for her milk. I know that with the generosity of Kevin's Cave people, we'll just crush that goal. Won't you help out today? There's a link to donate up here, or down there, or at any rate somewhere nearby. Thanks so much, and now back to the video. I got to the cave, and I knew that I had a couple of LMC 6482s on adapter boards for breadboarding. But I found that they're both in use with other circuits that I don't want to tear down. So I needed to mount at least one more for this demo. It's time to sit down at the microscope and get to work on it. Sorry about the video quality here. My microscope camera is a really cheap one that came as lagniappe with the microscope. I have the adapter card and pin headers held steady in a 40-year-old breadboard that I really don't care about. Getting the solder paste in place is always an exercise in frustration because my hands shake pretty badly. In particular, getting enough paste on that last pad in the lower left just wasn't happening until a huge glob came out. I had better clean that up. I got in there with a wooden pick to lift away the excess. Okay, that should be good enough. I pick the chip out of the tape and drop it into place, and of course I get it crooked. In with the fine tweezers to gently nudge it straighter. That'll do. I'm not too worried about the mess with the paste because reflow will take care of it. I'll get some heat on it. The right-hand side reflowed nicely. When I'm using the camera port on the microscope, I can't see through the left eyepiece, so I have no depth perception. I don't realize here that I'm blowing air past the chip rather than on it, but eventually I get it right. Watching reflow never gets old. It's magical how everything straightens out and the joints clean right up. Then to solder the pins. I often find I need to add the tiniest drop of solder to the iron, even starting with it tinned, to get good heat flow to the joint. But after that, the rule is feed the joint and not the iron. I didn't even notice that I accidentally cut the solder wire with the iron there. But as soon as the fragment contacted the drop, the surface tension drew it in, so no harm done. A few seconds with each pin and the job is done. I'll give the board a good bath with a soft brush and isopropyl alcohol, and we're good to go. So now I break out a breadboard and lay out the circuit that we just designed. You know how that goes, so I can do an extreme fast forward here. The pot on the left controls the input voltage, and I'm starting with a voltage very close to zero. The pot on the right controls the load resistance, and I'm starting with it fully counterclockwise so that the output is nearly a short circuit. Let's see what happens to the current as the input voltage changes. "584 millivolts gives 583 microamps. 1.19 volts, 1.19 milliamps. So far it's tracking really well. More voltages give us matching currents." Negative voltages work too. We get negative currents out. This looks pretty good. What about giving it a little bit of load? It starts out tracking pretty well. But with this load resistance, about 3 milliamps appears to be the limit. It won't push any harder than that. And the results are the same in the opposite direction. It's limited to 3 milliamps. What happens when we give it about 5K of load resistance? About 3/4 of a milliamp seems to be the limit. And with the full 10K load resistance, it gets stuck at 450 microamps or so. Let's sit down and think about what's limiting it. You probably already know what's going on. We set the sense resistor to 1,000 ohms. When we turned the load pot up to 10,000 ohms, we created a voltage divider with a series resistance of 11K. If the op-amp's output goes all the way to the 5-volt supply rails, the current through the sense resistor will be just under 0.5 milliamp. The circuit just can't push any harder. If the load resistance is very small, then the sense resistance will limit the current pretty severely. Most constant current loads are only a few ohms, so we should probably use a much smaller sense resistor and a smaller range for the input voltage. A worse problem is that the two ends of the load are each at a voltage driven by the circuit. There's no way using this circuit to deliver a current into a load whose other end is grounded. We can't quite fix that with this circuit topology, so let's try a different one. We'll start with the current sensing resistor, same as before, but this time we'll tie it to the positive supply rail. We'll use a PNP transistor as an element to regulate the current, and the load will be returned to ground as we want it. We'll have an op-amp drive the base of the transistor. The op-amp will monitor the voltage at the sense resistor, and our feedback loop will keep that voltage equal to a control voltage at the input. This configuration is the same as one that we've used on several other projects on the channel, but I want to do a deeper dive into the details. Let's start by building it just as I've shown, with potentiometers for the control voltage and the load. Once again, the schematic, plus some refinements I haven't shown yet, is on the project GitHub. The sense resistor is now 100 ohms, which should give us an output of 10 milliamps per volt. The pot setting the control voltage is wired to give a range from 0 to 2 volts below the power rail, giving an output current of 0 to 20 milliamps. Here it is on the breadboard. The control voltage is set for 0 current output, which is to say it's 0 volts below the positive 5-volt power rail, and we do get no current out. We can tweak the input voltage to various levels, and the output current follows, at 10 milliamperes per volt. But both the input voltage and the output current are jumpy. The readings aren't stable. Oh dear, I see what I did. I didn't put in the decoupling capacitors. Let's see if putting them in settles the circuit down. One capacitor on the positive supply and the other on the negative. Yeah, that's behaving a lot better. Now the output current tracks the input voltage pretty closely. This is an inadvertent lesson in what the decoupling caps do. Let's put in a little bit of load resistance. As we expected, there's a limit to how hard the supply can push. And 5 milliamps or so appears to be it at this load resistance. But I'm noticing that as I turn up the control voltage, the load current decreases rather than hitting a ceiling. I'm not quite sure what's going on with that. Let's see if the circuit simulation brings any insight. Here it is in CircuitJS. We see exactly the same behavior as we increase the control voltage. The output current climbs to a peak of a little over 5 milliamps, about 5.2, and then decreases as we continue to increase the control voltage. But the simulation makes it obvious what's going on. The pass transistor is fully saturated. The collector to emitter path looks almost like a short circuit. But the op-amp is continuing to set the current through the sense resistor. And the only way it can do that is to pull more base current. That in turn raises the base emitter diode drop, which has the effect of raising the collector to emitter voltage and pinches off some current to the load. What I should have done here is to add a resistor to the base, which will limit the base current. With the base resistor, the runaway current is gone, and the output current stays almost flat as I increase the control voltage. But that raises another concern. The sense resistor is seeing not just the load current, but also the base current. For a typical small signal transistor with a beta of 100 or so, that's about a 1% error in the output current, which is pretty tolerable. But a big power transistor might have a beta of about 40, and the 3% error or so might start to get annoying. We can fix both problems by using a P-channel MOSFET. It has essentially zero current at its gate, so it behaves almost perfectly with no possibility of runaway current. So I'll pull out the 2N4403 that I was using and replace it with a BS250P, which conveniently uses the same pinout. It mostly tracks well, but there are a few points where it appears to be oscillating again. But at least when we push to saturation, the current sag is gone, and I have a pretty good idea what's going on with the oscillation. The problem is that a MOSFET's gate often has a fair amount of capacitance. That can introduce enough delay in the feedback loop that the circuit will oscillate. We've seen the problem of driving capacitive loads before. Driving the gates of big MOSFETs is a whole topic in itself, but for this small one, we can get away with simply adding more frequency compensation. I'll replace the feedback wire with a 3.3K resistor and add a capacitor around the op-amp for fast AC feedback. Let's see if that helps. With that change made, the oscillations are cured again. The output current tracks the input voltage quite tightly indeed. The next problem that I want to tackle is that the input voltage is relative to the positive supply rail. Not only is this convention unusual, but it also means that the op-amp needs to be able to accept input that swings all the way to the rails, and whatever is driving the op-amp needs to be able to put out a voltage that swings all the way to the rails. That was the reason I chose the LMC6482. It's my usual go-to choice when I need an amp with rail-to-rail I/O and no special requirements otherwise. I can't do much about needing to read out the sense resistor close to the rail, but let's fix the input to use a ground reference voltage. I still have the other half of the LMC6482 available, so let's try to use it to translate the voltages. One of the most versatile ways to translate voltages is with a current source and a resistor. I'll put in an N-channel MOSFET ahead of the input and drive it with the same current source circuit, except that the polarity is reversed so that it's sinking rather than sourcing current. And I'll pull that current from a pull-up resistor. We know what that intermediate current will be. It's the input voltage divided by the sense resistor of this new current source. The only place for that current to come from is the pull-up resistor, so we can use Ohm's law to find the voltage drop across that resistor. And that's the voltage that determines the output current. So we have a nice linear relationship between the input and output currents. We can make the sense resistor almost arbitrarily small, and rescale the transconductance by choosing the right ratio of the two resistors in the middle. Let's make these changes at the bench. Once again, I've got a full schematic up on the project GitHub, so you can follow along on your own bench. I recommend that. There's no better way to learn electronics than to do it. Here on my breadboard, the results are so good they're boring. I can provide an arbitrary voltage, and the output current follows. But that 20 milliamp current is still pretty piddly. I really want to get to work on upgrading this thing to produce some respectable current. But I'm out of time for this episode, so that upgrade will have to wait for the next one. I hope you'll stay tuned for it, and perhaps let YouTube know that you want to see it. In the meantime, stay safe, stay healthy, stay curious, and please take care of one another. Bye!